Hello again, and welcome back to our statistics series for ENIGMA-U. Today, we're going to be talking about z-scores, which is a way to standardize our scores and distributions so that we can compare our data meaningfully to other data sets. We're going to talk about what z-scores are, how to use them, and some other cool applications for z-scores. So let's get started. Oops, I always do that. Okay. So some of the tools that we're going to be talking about today are here, the symbols and concepts that we'll be using. The one thing that I'm going to point out is as we go through our lecture today and through the rest of our lectures, be sure to be looking out for the difference between population parameters in our symbols, those Greek letters, and our sample statistics, those italicized Latin letters. It'll help you as a learner and all of us kind of stay together with whether we're talking about a population or whether we're talking about a sample. Okay, so what are z-scores? By definition, z-scores are a transformed or standardized score that is going to specify the precise location of each x value within a distribution. And how it does that is it designates how many standard deviations above or below the mean that raw score falls. More specifically, z-scores just aim to make our raw scores more meaningful and more comparable. If the only thing that you have is your raw score, you don't really have that much information on where it falls within the distribution. So we put them on a standardized scale by transforming them into z-scores. And we'll talk more about this as we go. The purpose of a z-score is to, as we just established, identify and describe the exact location of each score in a distribution. If they're positive, it tells you that the score is above the mean. If they're negative, it tells you that the score is below the mean. And the numerical value tells us how far away from the mean it is. It is also helpful in standardizing an entire distribution so that we can compare scores from different distributions to each other, or when we want to compute probabilities of a particular score. For this lecture, we'll be talking more about how to compare scores from different distributions. Next lecture, we'll talk about how to use these scores to compute probabilities. So let's put this into a more practical example of why z-scores are important. So let's suppose that you have two different distributions of exam scores, maybe two different classes who took the same exam. Suppose you received an exam score of x equals 76. That's your score. And you want to know how you did in comparison to your classmates. Your raw score of 76 doesn't really tell you much. It could be one of the best scores or it could be one of the worst scores. You don't really know. So to find the location of your score, you need to have information about all of the other scores in the distributions. So for both distributions, let's say that the mean is 70, but for one distribution, the standard deviation is 3, and for the other, the standard deviation is 12. Oh, excuse me. In this first distribution, 76 is you're going to be 2 standard deviations above the mean, which is awesome. In the second distribution, you're still above the mean, but you're only 0.5 standard deviations above the mean. So basically, this slide is just to highlight that raw scores can only tell you so much. A z-score is going to tell us where we are in position or relative in position to the other scores in the data set. So converting let's talk about some of the properties of z-scores. When we convert a distribution of raw scores into a distribution of z-scores, it's not going to change the shape of this distribution at all. For example, if your original distribution is symmetrical, your z-score distribution will also be symmetrical. If your original distribution is positively skewed, z-score will be positively skewed as well. However, all z-score distributions will have a mean of 0 and a standard deviation of 1. So it'll look like this. You should think the units, the reason why this x-axis of our z-score distribution are 1, 2, and 3, and negative 1, 2, and 3, is because the units of a z-score distribution are standard deviations. That is the units of z-scores. And we'll get more into that in a second. So let's talk about how to do this transformation. How do we transform raw scores into z-scores? The numerator is going to be a deviation score, which we've seen before. This is the same thing. You're just finding the distance between your raw score and the mean. And it also is going to indicate whether the x value is located above or below the mean. If your numerator is positive, your x score is above the mean. If it's negative, it's below the mean. And then you're going to divide your deviation score by standard deviation. I said deviation like 6 times just then. You're going to divide your numerator by the standard deviation. So because we want the z-score to measure distance in terms of standard deviations. Like we said before, we want standard deviation to be our units. Let's look at an example here. Let's say that we have a mean of 69 and we have a standard deviation of 3. Okay. Our x value is 74 and we want to transform that into a z-score. We'll plug it into our formula here. We'll take our raw score minus our mean over our standard deviation, and we're going to get 1.67. What that means is your raw score of 74 is 1.67 standard deviations above the mean. Let's look at another one, but changing the standard deviation. Now our standard deviation is 8. If we plug it into our formula, now we get a z-score of 0.63. That means that 74 in this distribution is only 0.63 standard deviations above the mean. Even though it's the same raw score, since your distributions have different standard deviations, your z-score is going to be different. Let's look at an example of when our raw score is below the mean. We're going to put that into our handy dandy formula. If your x value, your raw score is below the mean, then you're going to get a negative z-score. So negative 2.33 means that the raw score of 62 is 0.233 standard deviations below the mean. If for some reason your raw score exactly equals the mean, then your numerator will be 0 and your z-score will be 0. It is 0 standard deviations above or below the mean because it is the mean. Right there. Okay. Let's talk. Another thing that we can do when we have that formula is we can actually find a raw score from the z-score. As long as we have the mean and the standard deviation, we can calculate our raw score from the z-score. The way we have to do that is we first have to algebraically solve for x using this formula. So if we did a bunch of transformations here, then we would get x equals the standard deviation times the z-score plus the mean. Let's look at an example of this. Say you have a distribution where your mean is 13 and your standard deviation is 4. You know that your z-score is 1.78. So you know that the score is 1.78 standard deviations above the mean, but we want to figure out what that raw score actually is. We're going to plug it into this formula and we're going to get 20.12, which means that your raw score is 20.12. Just cool that it can go both ways. You can do the same thing if your z-score was negative. Just plug it right into that same formula and you get your raw score of 11.64. Okay. The other thing that we can use z-scores to do is creating other standardized distributions. Oftentimes when we when we have two different distributions, you can't compare the raw scores to one another. That's often because for example, if one distribution is symmetrical and one is positively skewed, or even if they're both symmetrical, they have different means, they have different standard deviations. Two raw scores from two different distributions aren't going to tell you very much. But if you put both of those different distributions, if you transform them into z-scores, then you can compare those two raw scores from two totally different distributions because you know how many standard deviations above and below the mean each of those scores is. So we use z-scores because it makes it possible for us to compare different scores or different individuals, even if they come from completely different distributions, which is amazing. The reason for this is because they'll always have the same shape, the mean is always 0, and the standard deviation is always 1. So they're easily comparable to each other. Allows direct Z-scores allow direct comparison of scores from two different distributions because they have been converted to the same scale, standard deviations. Following a Z, this is kind of what it looks like when we use Z-scores to standardize a distribution. So right here, we can see that following a Z-score transformation, your x-axis is going to change from x variables or x values to standard deviations. That's the change that we made. Here we have a population of x values. We transformed them into z values using that formula. The shape is the same. The only difference is the mean is now 0 and your values are now in standard deviations. And it's the same thing if you were to do this on a bar graph or any other type of graph. Okay. So although z-scores have a lot of really awesome things that we can do with them, like comparing scores from different distributions, finding proportions, things like that, a lot of people don't like working with z-scores. They find them a little bit cumbersome because they contain negative values and they contain decimals. So for this reason, it's actually pretty common to standardize a distribution by transforming all of the scores into a new distribution with a predetermined mean and standard deviation that are whole round numbers. Standardized scores like this are frequently used in different types of psychological and educational testing. So for example, if you took the SAT or if you've ever taken an IQ test, your score is standardized with a mean of 500, standard deviation of 100, or with the IQ test, a mean of 100 and a standard deviation of 15. We also use this when we do T-scores and when we use scaled scores. And the way that we do it is we use the Z-score transformation as kind of like a middle step. You take your original raw scores, you transform them into Z-scores. Once they've been transformed into a Z-score, you take all your Z-scores and you transform them into new X values with the specific mean and standard deviation that you want. And there are different value or formulas that you can use to do that. We won't really go so much into it, but just so that you know this is a possibility. This is just a diagram that shows how a z-score and a z-distribution acts as an intermediate standardizing step. You take your original scores here, transform them into z-scores, and then you transform them into, for example, your target distribution with a mean of 50 and a standard deviation of 10. And that can just help scores be easier to look at and compare. The last thing we're going to talk about today is that up until now, we've talked about how to use z-scores with a population, but it's also possible to compute z-scores for samples as well. And z-scores for samples will tell you the same thing that it tells you for a population. It indicates your relative position, the relative position of a score in the sample, and it indicates the distance from the sample mean, instead of from the population mean. The formula that you're going to use is pretty similar to the formula that you would use transforming a population into a z-score. The only difference is that you're using sample statistics instead of population parameters. So instead of the population mean, you're going to use the sample mean, and instead of the population standard deviation, you're going to use the sample standard deviation. The rules are all the same though. The sample z-scores will have the same shape as the original sample. The sample z-scores will have a mean of 0, and the sample z-scores will have a standard deviation of 1. Okay, and that's all for now. When we join each other again, we will be talking about another way to apply z-scores by finding proportions for our data.